Hello, everyone, and welcome to the second Agda lecture of the HoTTEST Summer School 2022. Today's lecture will again be by Martín Escardó. Let me introduce him properly. Martín is a professor at the Computer Science Department at the University of Birmingham. He has a very wide-ranging research interests, including computability, univalent mathematics, domain theory, and the list goes on. It's a great pleasure for me to introduce you today, Martín. Please take it away.
Thanks, Egbert. Hello, everybody. So in this second lecture on Agda in the summer school, I want to do in Agda what Page has done in type theory syntax before. So Page introduced some constructions like Cartesian products, sums, function types, sigma and pi types, and identity types. And I want to do all this again in Agda. This is a page from the handouts. So if you click here, you can see the handouts later when you revise after the lecture. In this lecture, I'm going to take a selection of the material of this handout. And I will also try to emphasize the connection of type theory with logic. Actually, it will be the case that most types and type constructors, they have a dual interpretation. Sometimes, for example, the Cartesian product can be interpreted as a mathematical object. So you take, for example, A and B can be the reals, and if you do the reals times the reals, then you get the plane. But when we consider propositions as types, if A and B are not the reals, but some mathematical statement, like, I don't know, there are infinitely many primes, which, by the way, we're going to try to formulate in Agda at the end of this lecture if we get there. So when you have two mathematical statements, A and B, written as types, then A times B actually will be interpreted as A and B. And we're going to see how this works. It has already been mentioned by Page, but we're going to do it in Agda. So let's start by first revising some of the types that we saw in the first lecture. So the simplest one is the empty type. And now every type comes with an introduction rule, as you have seen in type theory, and constructors. The empty type actually doesn't have any constructor. So that's the complete definition of the empty type here. And so we need to say what the elimination principle is. So if you look at the mathematical reading of the elimination principle, so if you have a family of types indexed by the empty type, and we want to produce a function like this. So actually I should remind you, I should write this. Actually this dependent type in the terminology of Page's lectures on homotopy type theory is actually written as a pi type like this. So that's the Agda notation for the pi type, and we're going to come back to this. So you can define a function such that for every element of the empty type is sent to an element of AX. But of course, there isn't any element in the empty type, and that's why it's called empty. And so there is this special way in Agda to say, okay, I'm not going to give a definition actually of this function because there are no constructors in the definition of the type. Okay, so this type may seem a little bit silly at first sight, but it's actually very important. For example, we can use it to define negation. So remember that in proposition as types, we saw in the first lecture that this is interpreted as false. And so the negation of a mathematical statement A, or a type in our case, is just a function that maps elements of A to the empty type. And such a function, at least intuitively, you can see that such a function can exist only if A doesn't have any elements or if A is empty. So in fact, it's sometimes convenient to have a synonym for this negation. So I say that the type A is empty if we have a function from it to the empty type. Later, when we have more axioms, we can show that this is equivalent to actually A equals the empty type, or A is isomorphic or equivalent to the empty type. But for now, it suffices to define it like this. Now, whenever we have an elimination rule like this one, there is always a non-dependent version. So notice here that the output of the function depends on the input x. So if you want this dependency not to exist, you just have a function from the empty type to A, right? So there is, in fact, a unique function from the empty type to any type, and is a function that has an empty graph intuitively. Now, this is actually a special case of the elimination principle, because we use the family, which is always this given type. Maybe for clarity, I could call this one B. Let's call this one B. And then what happens is I take my family A in the definition above to be the function which is constantly B. Yeah, and so if you take the function that is constantly B, then we get this. And in fact, the reason for this is that a function type like this, x arrow b, and we're taking x to be the empty type, this is actually the same thing. Maybe I should use dot like in Egbert's book for definitional equality. So that's the same thing as pi x in x of b. So it's the family that doesn't depend on x. So which is the same family here that we take. Okay. So let's do a very simple proof here, but actually maybe I can do it again. Let's start from scratch so that you see how Agda works interactively. So I want to prove that the empty type is empty. So let's do a third proof here. Let's prove that the empty type is empty. So let me copy this for the sake of speed. Okay, so what can we do here? Okay, so Agda says, well, okay, you have to prove that the empty set is empty. So one thing we can do here is press Control U, Control U, Control U, Control C, Control comma. And what this does, it unfolds the definition of the goal. So if I press Control C, Control comma, it just tell you that you have to prove what you said you wanted to prove. But if you do Control U, Control U, Control C, Control comma, then this simplifies the goal by applying all the definitions as much as possible. So this simply unfolded the definition of is empty. So we need to produce a function from empty to empty. And there are two ways to do that actually, which I have written here. So one is the identity function that we defined in the first lecture. So that's the identity function, who outputs the same thing as it's given. So what did I do to do this? I pressed a meta dot, and this takes you to the definition, and you can keep doing this, and you can pop from the stack, so to speak. You can do meta comma, and this goes back. So meta dot goes forward, and meta comma goes back.
Martin, 1 second. I want to tell people to ask questions in the Q&A as opposed to chat. A lot of people are asking questions in chat.
Yeah, the Q&A is better because the questions get recorded and then can be answered independently by different TAs. Okay, so that's one way, is to use the identity function. And the other way is to notice that we can use the non-dependent elimination principle, because the non-dependent elimination principle gives a function from the empty type to any type. Okay, or you can just write an identity function here explicitly. And there is actually another way. So I can actually, okay, so let's show the Agda commands here. Another way is to do Control-C, Control-R, which is refine. And so it refines like this, and it says, okay, so now I can try to pattern match on X. No, I cannot pattern match on lambda, but I can write it manually. So I can write it like this, lambda, and then I say open close brackets, which is similar to the use here, which says, okay, Agda, where is it here? There is no input because the input is the empty type. Okay, so that's a third way to prove that. Okay, so so now let's revise the unit type. So the way I did the unit type in the first lecture was different. So I used, if you remember, I used a data definition, so that we declare that the name of the type is 1, Blackboard 1, and we say it's a type, and then we give a constructor, we call it star, it's an element of the unit type. But another way to do that is to use a record. I'm going to explain a little bit better why sometimes it may be more convenient to use records when I have a second, more elaborate example. And then this record is going to have a constructor star. You can imagine this definition to being almost the same as the previous one. There's going to be a difference, which I'm going to explain later. And in order to be able to access the constructors of a record, we have to open it. It doesn't need to be public, so you just open it. But when you open it public, then anybody who imports this file, for example, people doing exercises based on the lecture, don't need to open it again because it's open for them. Okay, so now let's do a slightly more complicated example. Let's try to prove that the empty type, the unit type 1. Yeah, so actually let's write this here. The terminology is unit type. So let's try to show that the unit type is non-empty. So that we learn how Agda works. Oops, sorry. I did something. Press the wrong keys. Okay, so I'm going to copy this and I want to prove this. Okay, so, okay, I already have this name, so I need a new name. So let's call it prime. Control-C, Control-L to load the buffer. Okay, let's look what the context says. Well, it says, so now I do Control-U, Control-U, Control-C, Control-Comma. And it says, okay, so what should, if you unfold the definitions of not and the definition of is empty, that means that you have to, given any function from the unit type to empty, you need to get an element of empty. Now, you may wonder, where would you possibly get such a function from 1 to the empty type, right? Because there is nothing to map star to. But if it were given hypothetically, so let's give it as a hypothesis. Okay, suppose this function existed. I'm going to call it lambda f, and I'm actually going to give the type it has for the sake of clarity. And I'm going to fill this hole like this. So that's the function from 1 to the empty type. Okay, so now we need to produce an element of the empty type, which is in principle impossible, but here it is possible because we have this hypothetical function f, which maps anything in the unit type to f. So I can do f, And now I do refine. And now I see I need to produce an element of the unit type, but this is a star, so I'm done. Okay, so that's how you can use Agda interactively to do such proofs. You choose which one of these two proofs is more readable for you. I probably prefer the second one, but I don't mind either. Okay, so now let's look at the complete definition of the unit type in Agda. So we also need to define the elimination principle. And so the elimination principle always has the same pattern. If you remember, for example, when we did the elimination principle of the empty type, so you needed to show that for every element of the empty type, a proposition holds. And we did the same actually last time for the natural numbers, and the elimination principle was the principle of induction on natural numbers. And so the conclusion of the elimination principles is always the same, but of course you change the type to be whatever type you're considering. So what changes is the hypothesis needed to prove the conclusion. So what are the hypotheses that you need if you need to show that every element of the unit type satisfies some proposition? Yeah, so we represent or this predicate, if you want, predicate A. So we, in propositions as types, we represent predicates as functions whose values are types, because we want the values to be propositions or mathematical statements. And so if you want to show that this predicate holds for every x, then it's enough to show that it holds for a star. And the reason is that the unit type has only one constructor. So let's actually erase this definition here. Okay, so one thing you can do is in any hole, you can refine. So let's Control-CR. Okay, so it has an X. Okay, sometimes I prefer not to have a lambda. So after refine, I actually transform this into a definition of this form. So the A here is the element of A star, and not, yeah, the element of the type A star. So if you like, a proof or a witness or evidence that A star holds. And then we need to be given this X. Okay, so now we can use the same technique as in the same lecture. We can pattern match on X or do case analysis on X. So there's only one case. So I do Control-C, Control-C, and I say I want to split in the variable X. And then Agda looks at the definition of the type, and it looks, okay, so there is only one constructor. So it replaces the X by this constructor. And now you need to produce an element of A star. And you have it because it's the given hypothesis. So this hypothesis here. So you can just write here A and then Control-C, Control space. Let's look at this proof again. So when I wrote star for X, and then I wrote A inside the hole. Let's see if I can write A inside the hole now. So Agda actually accepts it. And so this is kind of magic. So let's redefine this type using data here. Okay, so now Agda doesn't like this proof anymore. It says star is different from X, okay? So what's going on here, so let me undo all this here, is that record definitions satisfy a certain iter rule. Yeah. Now the iter rule for this particular record says everything in the unit type is definitionally equal to star. Okay, so that's the iter rule for this. Well, I'm going to show you the iter rule for other types so that maybe you can learn from analogy first what these iter rules are. But what they make is some proofs more convenient. So here we don't even need to pattern match on X because Agda knows, because you have used the record, that every element of the unit type, I repeat, is definitionally equal to star. This makes sometimes things a little bit more convenient. It allows you to omit 1 or 2 steps of a proof sometimes. Okay, so, and then again, like before, so if we don't have a dependent function, we have just a normal function, which means is a dependent function where the output actually doesn't depend on the input. Then you get this elimination principle that says, if you give me an element of A, then I can produce a function from the unit type to A. And they just use the same definition. Okay, so let's do more examples of this pattern. So this is like the Booleans. I'm going to define a type isomorphic to the Booleans. So I said the type, I call it blackboard 2 with bold element 0 and bold element 1. So these are the 2 elements. And so let's look at the elimination principle. So again, the conclusion is of the same form as we had in all elimination principles, as I mentioned before. But now you have to think, okay, so what do I need to do, or what do I need to assume if I want to prove that for every x in 2, A of x holds? Well, you will need to prove A for each element of the binary type 2. So you need to prove A of 0, or you need to assume A of 0, and you need to assume A of 1. Okay, so let's delete this proof actually. So, and let's do it from scratch. So I have this implicit type here that I'm going to try not to write down here, but I remind you, if I wanted to write it down, I could do it like this, but I'm going to always try first without mentioning A. So I'm given an element of this type, x0, an element of this type, x1. Maybe I should call them a0 and a1 for clarity. And now I'm given the x. Okay, so now that's going to be a little bit different from the previous case, where I could just answer A right away, because I need to produce an element of A of x. But what A of x is depends on x. So I need to know what x could be. So then I do case analysis on x. So I press C, x in the hole. I do Control C, case is split. And so now let's look at the goal here, Control C, Control comma. So the goal is to prove A0. So now what is happening here is that Agda is applying substitution along definitional equalities. So when x is actually 0, then this becomes A of 0. And so this is why Agda says, okay, so you need to prove or to witness A of 0. But now, if you look at the goal, you can see that this is available here. So you can either type it directly, A0, Control C, Control space, or I remind you, if you're lazy, you can do Control C, Control A, which is auto. This saves you some typing sometimes. When Agda, this Agda sometimes can figure out what it is. So in this case, it's not very difficult to figure out because it's already available. So Agda says, okay, I'll just give what is available. And here again, so the substitution now is for x becomes 1. So you need to produce an element of a of 1, which is available. So I do Control-C, Control-A, and then here is my proof. Okay. So that's sometimes people call this elimination principles. They call them induction principles, even though there is no induction, but by analogy with the natural numbers. Yeah. In the natural numbers, you want to prove something by induction, you need a different hypothesis. And again, you have the non-dependent version of this elimination principle. Now, this is basically if then else. If you identify one of 0 and 1 with true and the other one with false, so that will be like the then branch, the else branch, and this is the condition. Yeah. So, but the condition is written last rather than first as usual in if then else. And this and the dependent version of this is what we called the dependent if then else that we saw in the first lecture. So the dependent if then else is nothing but the eliminator of the Booleans. So that's what the dependent if then else is the elimination, the elimination principle. And if then else non-dependent is just the non-dependent version of the elimination principle. Okay, so now it would be a good point if people have questions about these elimination principles.
Oh, Martin, there's a very good question, which is just a bit off topic. And the question is, when Agda does pattern matching, does it internally unfold it to eliminators?
It unfolds it to a case tree. So case is a little bit like eliminator. So in the internal Agda, there's something called case that corresponds to the eliminators. But yeah, that's a very good question. So I can say something else as well. So the eliminations are very important in order to understand what type theory is. But they're very inconvenient to use in practice for several reasons. And so people propose then, okay, so instead of using eliminators, let's use pattern matching because it's more readable. And then people prove theorems that actually definitions by pattern matching are equivalent to definitions using eliminators. Yeah, and then in Agda, this is translated, the pattern matching is translated to something similar to eliminators, which are the cases. And this is true also when we use the identity type that hopefully we will discuss today in Agda. But the original proof of that, close to the end of the last millennium in the 1990s, I think it was proved by Conor McBride in his thesis, I'm not mistaken. But so if you assume the K axiom, this is what he did in order to prove that definition by cases, by pattern matching on the identity type is equivalent to using eliminators. But the K axiom that maybe we'll discuss later is not good for homotopy type theory. And so we needed a new theorem for that. And we needed a new implementation of pattern matching in Agda, which is triggered by this flag here. And the theorem by Jesper Cox is that definitions by pattern matching on the identity type are equivalent to definitions using the eliminator of the identity type, which is called J. I may revisit this discussion when we go back to the identity type later. This was
but I do also want to just make a comment that Agda has what is called a termination checker algorithm. And in the general case, the termination checker algorithm knows if something is terminating, but this does not correspond to eliminators in an evident way. I have seen very weird termination checking acceptance things which it take like hundreds of lines to unfold in terms of eliminators in very non-obvious ways.
Yeah, so it's tricky to convert recursive definitions with pattern matching to eliminators. Basically, this is what you're saying. And then any proof of such a theorem should include this possibility as well, right? But yeah, so this was an excellent question. So feel free to ask questions anytime. We can discuss this more on Discord if people want to know more about that. Okay, so let's go back to here. So what this means is I'm showing you these eliminators, but actually when I actually write Agda code to prove a theorem, normally I'm not going to use the eliminator. Sometimes I will because it's just more convenient. But when it is more convenient to use pattern matching, I will just use pattern matching in the knowledge that is equivalent to using eliminators. Okay, so now so let's go to this table here. So what is the progress we have made? Okay, so we did the empty type, and then we did negation. So I want to discuss products or pi types, or also called dependent function types. So these are actually, we don't define them in Agda, they are primitive. And as I mentioned before, the pi type is written like this in Agda. So it's written just like a function, but we indicate the input with a variable, and then the output depends on the variable. In Agda, you can also use the for all notation instead of pi, so that's allowed. And sometimes it's convenient to use the for all notation because the for all notation allows you to omit the type declaration. And if you're lucky, this will work because Agda will infer the missing X. And then you can sometimes, when the type is very complicated and you want to omit it, you can it. Normally, personally, I prefer to add as many types as possible so that things are readable. But sometimes it's actually better to have a concise definition. If you're only talking, let's say, all the time about the natural numbers, you don't need to keep writing this. So now, sometimes I prefer to use pi syntax. Most of the time I prefer not to use it, but sometimes I prefer to use pi syntax, and you can introduce it as follows. So firstly, I'm going to define pi. I'm going to say, okay, so what is pi? So pi takes a type. I call it X here, but now I'm calling it A. And then a type family indexed by A, so it's called B. And so I say pi AB is simply the primitive pi type of Agda. So the dependent function type. And now, once I have defined this, I can use a special syntax declaration, which for some reason is written backwards. So normally you say something on the left is defined to mean something on the right. But here, for some reason, the developers decided to write the define notation on the right. And so whenever Agda sees this, it's actually going to interpret it as this, which actually is the same as this. Yeah, so the effect of this is that really this notation here becomes equivalent to this. Now, unfortunately, you cannot use the colon, which is used for type the declarations of Agda, so you need to use a new symbol. And now Unicode is notorious for having different versions of the same symbol. And for this, you have to type it using, in Emacs, you have to type it using backslash. And then if you see here, very small at the bottom, you have lots of options. So one of them is colon. And now for colon, there are several kinds of colon here. I have chosen 4 because it's very similar to the normal one. And that's the reason why several of you wouldn't make this choice, because it looks the same. But actually, I prefer it to look the same because it's the same. It's just that Agda is not allowing you to use the same. Okay, but we could have chosen something else. But be aware that you have to type this as in this like in Emacs. It's a different symbol actually in Unicode. Okay, so now we've been talking about dependent functions a lot. So let's look at function composition. Actually, let me hide this. Okay, fantastic. So I'm going to define function composition twice. I'm making a trick here. So in Agda, you can define a new module whenever you want inside your module. I could call it blah here, but because yeah, I'm just not going to use this module, so I call it underscore. So that's a fourth use of the probably 10 uses of underscore in Agda. So that's called an anonymous module. But I'm going to make the things in the module private so that nobody can see it outside the module. So this is only useful for teaching purposes. Okay, so here is my definition of function composition. I have a function G, which is of this type, B to C. And then I have a function F, which is of this type, A to B. So I want to do G after F. So this is G after F. So that's, okay, so that's a function from A to C. So I give the input here, and now I need to do the output. So it is exactly as I said. So you do F, and after that, you do G. So that's the normal composition that you have seen in any basic mathematical course or even computer science course and in programming. But we can have actually a dependent version of this. So we were going to change these functions here that are non-dependent. We're going to change them to dependent functions. Now, I could give this as an exercise. It's a hard exercise. So figure out how dependent you can make these functions when you do G after F. Yeah, I want to actually have the same definition. I don't want to change the definition, but I'm just going to tell you the answer. And I'm going to write it using pi, just to illustrate that we can use this syntax. We can change it to the normal Agda syntax after we finish if we want. So I'm going to change the function from B to C to a dependent function. So for every y in B, C of y. So I make this one dependent. I'm going to keep this one the same. And I'm going to change this from A to C to be a dependent function. So now it's pi x in A of C of f of x. And this is the same definition. Now you can actually think, you should actually think after the lecture, if you haven't seen this before, whether you can make it even more general, more dependent. So for example, you can think, why didn't I do anything here? Yeah. And then you can try to discuss this in Discord in the Agda channel or in the HoTT channel, because this is nothing particular to Agda. This is about type theory really. And now the understanding of this is that it's just function composition. But if you look at the propositions as types, interpretation of mathematics, so mathematical statements are interpreted as types, this actually is the proof of an intuitive fact. So if for every y in B, it is the case that C of y holds, and you have a function from A to B, then, of course, it is also the case that for every x in A, C of f of x holds, because an f of x is something in B. Yeah. And so this is an example of something that has a dual interpretation as an operation on just types interpreted as collections, if you like, Or the second interpretation is types interpreted as mathematical statements. So lots of things we are going to write down in Agda or in type theory on paper, they have this dual interpretation. And the proof is just function composition. Yeah, we can try actually to do this proof again. So, okay, so the inputs are G, which is of this type. Actually, let's write this now in conventional Agda notation. I just wanted to illustrate. The pi notation here. So X in A. Let's see if this is still type checks. No, there is a bracket missing here. Okay, Control C, comma. Let's see the context. Okay, so you need to produce an element of C. So how would I do the proof if I am just playing a computer game and not thinking too much? I say, okay, so I need something whose output is C. Let's see what can we use. Well, we have G whose output is C. So I can do G and then I refine. Look at the context. Okay, so now I need a B. The only thing that can produce a B is F. Okay, so let's do F. And then I need something of A. Okay, I have, it's the X. Yeah. Sometimes you see people doing proofs like this. Have no idea what you're doing, but you just keep playing with the context. It can work sometimes. Okay, so now let's define sigma types. Okay, maybe I should pause here if somebody has a question about dependent function composition and pi types. If not, then I'll proceed to sigma types. Okay. So again, there are two ways to define the sigma type in Agda. One is using a record, which is the one I'm going to use. And then the one is using data. The one using data has some advantages for teaching purposes. So first of all, I'm going to make the first argument of sigma implicit because most of the time it can be inferred. I could make it explicit if I wanted to. And now, what is a sigma type? Well, the element of a sigma type is going to be a pair of elements that usually you separate by comma in usual type theoretic notation. But we are going to interpret this comma as a binary operator that takes two things and combines them. So the first thing is an element of the type A. And the second thing is an element of the type B. But B depends on A. So we need to have here B of X. Okay. So that's a dependent pair. Is a pair whose second element, whose type of the second component depends on the element in the first component. And now you can define the projections of this the sigma type. Let's see, before we look at the type, let's look at the definition. So the definition says the first projection gives you the first coordinate of the pair, and the second projection gives you the second coordinate. Now, if we're using usual Cartesian products, not dependent pairs, something like this, the type of the first projection would be this, and the type of the second projection would be this. But that's not possible. Well, first of all, let's see what the input is. Well, the input is not this, but is sigma AB. We don't need to write A because Agda infers it. Now, the output can be A, just as before. And that's because if you look at the definition of the sigma type here of the pair, the first component of the pair has to have type A. Now, the second projection gets much more complicated. So if you have a Z, which is a pair in the sigma type, what is the type of the second component? Well, is B of X. So, but what is X? Well, X is the first component of Z. Yeah. And so you need to do the first projection. Yeah. So the type of the second projection is this one. In recent versions of Agda, you can actually write this notation, if I'm not mistaken. You can say for every X and Y in the sigma type, and then you can say this. Okay, I need to delete this. It didn't work. A record. Oh, we can do this if we had defined it with a record, but not with data. Yeah. So we need to actually write. So if we had used a record, we would be able to do that. So we are forced to write it like this with data. Okay, so that's the definition of the type. Okay. Sometimes if you're not clear about the types, you can actually write question marks in the types. Let's see if Agda can figure out here what it goes. No, actually cannot. Control C, Control S. Solve constraints doesn't work. Let's try Control C, Control A. Also doesn't work. Okay, so in this case, you have to think. So PR1 of Z. Now, the definition I'm actually going to do is different. So I'm going to use a record. So the parameters for the record are the same, a type and the type family. And this produces a new type, just like the data definition. And then I'm going to have a constructor, just like in the data definition. I don't say its type, and instead say what the fields are of the record. So the field is going to be the first field here is going to be the first component of the constructor, and then the second field is going to be this. Now this may sound a little bit strange when you see it for the very first time. So these fields are the contents of the record, so there are two things, and you name them PR1 and PR2. So the effect of this is that Agda will automatically use the fields of the record as the names of the projections. So the projections will actually automatically get this type. So let's check that. So I'm going to define PR1 again, question mark, PR1 again, equals PR1. Oh, I need to open it public. So this is done here. So let me open it a little bit further up here. So now hopefully here Agda can infer the type, Control CS. Yeah. So then let's do PR2 again. Need to delete this type. Control C, Control S, solve constraints. Oh, silly me. I should have changed this to PR2, of course. Control C, Control S. Okay, so then Agda can infer the type here automatically. So this the projections are given to you automatically. Yeah. Now, this is one effect of having the record definition. Another effect is that definitions using record as opposed to data, they satisfy this ITER rule that I mentioned before for the unit type. And the ITER rule for the sigma type, it says every element of the sigma type is a pair equal to the first projection followed by the second projection. Okay. So this is the ITER rule. So Agda knows that everything in the sigma type is a pair like this. And in fact,
Martin,
yes,
there's a very good question and a follow-up. The first question is, why don't data definitions come with an ADA rule?
I don't know why the Agda people decided to design Agda in that way. This is a question we should ask the Agda developers.
But I mean, for example, what would an ADA rule look like for the natural numbers?
So the ADA rule for the Booleans, for example, is that any Boolean B equals if B, then true, else false definitionally. Yeah. I guess the eta rule for the natural numbers would, except that you cannot define them as a record, would be that every number is as zero or a successor, like we did if then else in the Boolean, something like this. But I'm not sure. I need to think offline. Don't want to improvise here in the lecture for this.
But there is like a fundamental issue that we can't pattern match a natural, we can't definitionally have that a natural number is either a successor specifically or is zero. So that type of ADA rule is impossible.
Yeah, because the data difference, so you can only use records in place of data when there is only one constructor in the data. So in the unit type, there was one constructor, which was a star. And here there is only one constructor, which is the comma. And then the reason is that then you list the arguments of your constructor as fields of the record. But if your data has more than one constructor, like the natural numbers that they have zero or successor, then you cannot do this in a record. Yeah, because the record can only list one option of things. You don't have alternatives in records.
And another question was, suppose that you did something like using the natural numbers eliminator where you sent Z to Z and S to S, and then you applied that to a number. That's not definitionally the same as the number.
No.
But would that be computable, or would it be possible to have a type theory in which you have that?
Maybe you can scratch your head and design a type theory in which this works. Yeah, but this is not what is happening in the underlying type theory of HoTT, which is Martin-Lev type theory. Yeah. So in Martin-Lev type theory, the eta rules are optional. Yeah. Some people consider Martin-Lev type theory with the eta rules, and some people consider them without the eta rules. In the HoTT book, the eta rules are used, and now maybe Egbert can correct me. You don't use eta rules in your book, do you?
No, I proved them.
Which is fine. Which is fine. But I mean, it's important that people are aware of this, right? That there is a possibility of having them or not having them on paper and also in Agda. Okay.
Oh, I guess another question that just got answered is, can you define the identity type as a record?
Don't know. Haven't thought about this. I guess the eta rule will be something like the K axiom, yeah. So even if you can, we don't want to do that in HoTT, yeah. Okay. So now let me come back to this, to the thing I tried to do before. So I can actually use patterns whenever the type is defined with a record, and so I can write the type of the projection like this if I want to. Okay, in the record definition. And the reason this is possible is this eta rule that says that every element of the sigma type is a pair. And again, we can use the same notational device as we used with pipe. So I introduce the sigma here, making the argument explicit, so that then I can write the sigma in the usual notation. And again, this is \4:: okay, to type it. It's the same as for pi. We're allowed to use the same symbol. And usually I'm going to write the sigma type either like this or sometimes like this. Yeah, so I consider the sigma type as the sum of the family. Okay, so let's now do an example. So recall that in the first lecture, we defined this dependent type as an example D. So D of true is the natural numbers, D of false is the Booleans. Then an example of sigma B in bool of D of B is the pair true 17, and another example is false true. Yeah, so that's exactly what happens with dependent types. The type of the second component of a pair depends on what the first component is. So if the first component is true, then the type is N. If the first component is false, the type is bool, and that's why we have to write we can write 17 and true as examples of this. Okay, so these are two examples. So let's look at the elimination rule. As I said often in this lecture, the conclusion of the elimination rule is always the same. You want to prove that for every element of the new type you have defined, in this case, the sigma type, you want to show that for every element of this type, some property holds. I call it C here. So here is the property, then properties of the sigma type. And the question is, okay, so suppose I wanted to prove this. What is the hypothesis I need? Well, you need to know that for any given A and for any given Y, so for any given element of A, X, and every given element Y of B of X, we need to prove that C holds for the pair. So if you proved it for all pairs, then you prove it for all Cs. Now, people may get confused that maybe this depends on the ITER rule. No, this doesn't depend on the ITER rule. This elimination principle would be provable using data or record. Okay, so that's not an issue here. And okay, so suppose now I'm given this hypothesis that for any given X and any given Y, C of XY holds. How do I prove that for any given Z, this holds? Okay, so let's actually do this proof here ourselves. So I called F the element in the type of this line. Now I load the buffer, and now I do pattern matching on Z. Why do I do this? Well, because Z is an element of the sigma type. So I do Control C, Z. Okay, so now Agda invents names I'm not very happy about. In this particular example, Agda calls them PR3 and PR4. So if you look now, PR3 is an element of A, so I'm going to call it X. And PR4 is an element of B of X, so I'm going to call it Y. Unfortunately, I need to rename the buffer. Now I need to prove C of XY, but then I can use F because F produces such a thing. So I can do here refine, sorry, F and then refine. Now it gives you two inputs, two holds. So one is for this input and the other is for this input. So if I do Control C, comma, I need an element of A, that's just the X. And for this one, I need an element of BX, and this is just the Y. So now half of you are mathematicians and half of you are computer scientists, and the other half nothing. So I don't know how to divide very well, as you can see. We have 3 halves among you. But for people in computer science and who know functional programming, this operation here is usually called carry. Yeah, when you carry a function. And not all the elimination rules can be inverted, but this elimination rule can be inverted, which means that not only this implies this, but also the opposite is true. So the conclusion of the previous elimination principle implies the hypothesis. And this is just encouraged. So let's try to do this proof very quickly. So the G is this function here. And now I have an X and I have a Y. And I need to produce an element of C of X, Y. And the function, the only thing I have there that can produce such a thing is G. So I do G, refine. Now I look at the whole here. And it's an element of a sigma type. A sigma type is a pair. So I can say, Agda, please refine. Okay, so it's a pair with two holes now. And then I look at the type of the goal is an element of A. I have it down here is an X. And I have it here as well. It should be the Y. Yes. Okay, so that's the sigma type. The sigma types are called sums sometimes. I'm going to explain why maybe today. Oh, maybe, yeah, I'm actually getting close to them. But before we do that, let's look at a particular case of the sigma type, which is the Cartesian product. So the Cartesian product is exactly like the sigma type, but the second component doesn't actually depend on the first component. In fact, some people have proposed to use the following notation for the sigma type. So the notation for the pi type in Agda is this, yeah. Some people propose to use this notation for the sigma type. Yeah, so be a kind of a dependent pair type. So like this, yeah. Yeah, maybe I like it. I'm not sure, but it's an interesting notation, yeah. But we'll stick to the notation of the books on type theory. Okay. So now that's, you can define the Cartesian product. So the pairs of elements of A and B using the sigma where the B doesn't depend on X. So the X doesn't occur here. But actually, if you wanted to, and we are going to do this exercise probably next time, you can see that actually the Cartesian product can be constructed using the pi type. So you get an isomorphic type if you do the following. So you have these two types. Now I define a single one. So here, this A now, the type of this is from 2 to type. So I do the product or the function space like this. And intuitively, okay, so if you write this in Agda, yeah, so in Agda, the notation is x in 2 to A of x, or should I use n maybe to be consistent with the previous line? Yeah. So how does this isomorphism work intuitively? So if you have two things here, you define the function that maps maps 0 to the first thing and maps 1 to the second thing. And if you have a function like this, let's say you have the function, let's say it's f. So then you map it. Oops. You map it to f of bold 0. How do you type bold 0? I forgot. So if you forget how you type things, you can do meta describe character. Describe character. And it says here how you type it. With Agda, you type it like this. B0. So, okay, so you do B0 and comma f of B1. And if you, that's the isomorphism going from this direction to this direction. And then,
Martin,
yes.
let me mention that there is a very quick command for using described character. It's CUCX equals. So try that out.
Yeah, I know, but sometimes it's very bad to remember CUX. Oh, what did you say? CUX.
CUCX and then equal sign.
Let's see.
CUCX.
C. Oh, when you say C is control?
Yeah, CUCX.
CUCX.
And then equal sign.
Equals. Okay, I'll try to remember that. Actually, these things, people, if you want to remember yourself, and it takes a little bit of time to get used to that, you can go to the Agda manual and then
there's the Emacs mode page in the Agda manual.
Exactly. Then there is somewhere, there is the Emacs mode, and then you will see the list of all these things. Okay, so.
Sorry, Martin, before you get back, you got curry and uncurry the wrong way around.
Oh, do I? Okay, I'll fix it after the lecture.
Thanks.
Sorry.
Also, I think we need to teach everyone something very important. You have that window there below. How do you close it?
Okay, so you can do Control X1 and then this becomes a unique window. You can do Control X0 here and it kills it, but I don't want to do it because it's going to mess with my this window here. So the one way to close it is just to load the buffer again. Yeah. So if you have a pair like this, then you map it. Okay, so you need to, if you have a function like this, you need, you have a pair like this, you need to produce a function. And then you map this to the function. Well, we can use the elimination principle. So it can do 2elim of A0, A1. If I'm not mistaken, this is what you can do. Or you can do a definition by pattern matching of a function f. We later will do this exercise in Agda, but so the intuition is here. But we need function extensionality. To prove that this works. Because you map f to the pair and then the pair to f, and then to show that the initial function and the new one are the same, you show that they are equal for each argument, but that's not enough to show that they are equal. Then, but applying function extensionality, then you get that they are equal. We're going to discuss function extensionality in a moment, maybe not today actually. Let's do a few more examples. So let's see if I can complete the Curry-Howard type. So I was planning to say that the sigma type has many uses, okay? But I'm going to say this later because now I want to get to, I want to complete the table and give you an example of a mathematical statement using all the things that we have defined. So we usually use plus for this, and I do it in my own repositories, but because in the first lecture I used plus for addition of natural numbers, I'm going to use dot plus only for these lecture notes. I'm not sure whether it was a good or bad choice, but this is the binary sum. And the binary sum is defined by two constructors. So the binary sum of two types. So they have this thing called an injection. So the idea is that let's have two types. Let's write them as sets, like a Venn diagram like this, and another type, and you do the union. But it's the disjoint union. In general, in type theory, in the style of Martin Leff, no two types have elements in common. So all the elements of any given type are elements only of that type. So this plus is the union, but it's disjoint union. And the in L and in right are the functions, the inclusion functions that include A into the union of A and B, and B in the union of A and B. Okay, so let's discuss the elimination principle, and let's delete the proof. So we need to prove that if we have a property, of elements of the union, we want to prove that for every element Z of the union, or I should say Z for the Americans attending here, but I'm teaching from Britain, so I say Z. So for every Z in A union B, C of Z holds. Okay, so what would be necessary to prove that? Well, this is the union of two things. So if I want to prove this, I need to prove that it holds for all the elements of A, and also to prove it to hold that it holds for all elements of B. And so what more precisely, for every X in A, I need to prove that C, I couldn't write here X. I have to say, I have to inject it inside the union. So I say that C of in L of X holds, and similarly, for every Y in B, C of in RY holds. Okay, so let's try to do this proof here. So I call this thing here F, and this one G. And so now I'm given the C, the F, and the G, and the Z. And now I need to prove this. Okay, so now I'm kind of stuck because they have two things that give me an answer in C, but one of them can only give an answer if I have an in left, and the other if I have an in right. So I need to case split the Z. So I need to know which of these two cases it is. So is it in A or is it in B? Okay, so let's do Control C, Z. I call this, okay, so X is an element of A and X is an element of B. So let's just write Y here and load the buffer again. So let's see what we need to show here. Okay, so if we are on the left, we need to show C of in left, but now we are in business because we have a function that knows how to do that. So I apply the function refine. I need the goal now becomes an element of A, which I have is the X. Yeah. And here is going to be similar. The goal is to prove an in right. And now I have the function that proves the in right. So that's G. So I do G of Y. Okay, so this is actually a definition by cases. Sometimes this plus elim is called cases. So I consider the case when it's in the left or is in the right. If it's in the right, you apply G. If it's in the left, you apply F. And this also has the non-dependent version when this thing is constantly some type C rather than C itself. So we have C is now a type, is not a type family. And now this is actually interesting when you read it logically. So logically, okay, so let's write it here. Mathematically, A dot plus B is disjoint union. But logically, it is OR, which is called disjunction. There are too many disj things. Okay, disjoint and disjunction not related. Okay. Now, why is that? Because the idea goes that how do you prove A or B? Well, we either prove A and then you're done, or you prove B, and then you're done. So you can either prove A, you do an in L, or prove B and do an in R. Okay, so that's what Martin Leff and before Curry and Howard and Brouwer and Heiting and Kolmogorov proposed as an interpretation of OR. But there is another OR that we're going to learn later, first in the HOT track, and I'm not sure whether also in the Agda track, which is we do a certain truncation to this normal OR operation. So this truncation, sometimes people imagine it as erasing information. So it erases which of the in L or in left, which of in left or in right you had. But actually the situation is much subtler than that. It doesn't erase information. It just identifies all the proofs. So if there are different proofs of A or B, it identifies all of them in a single equivalence class, if you like. But we are going to learn later the propositional truncation. But I wanted to say this now so that you are aware that there are two notions of disjunction. There is the first one that is this plus, and then there is the truncated one, and both have their uses. But it's important to have, and it's important to have both, as we're going to see later. In homotopy type theory. Okay. Now, the logical reading of the non-dependent elimination principle is the following. If you want to prove that A or B implies C, what you have to do is to prove two things. You have to prove that A implies C, and also you need to show that B implies C. Yeah, so this is one of the rules of propositional logic. So how you prove disjunctions. And similar to the case we had above with pi, we can see that the sum, the binary sum, is also a particular case of sigma. So the binary product, the Cartesian product, was a particular case of pi, and the binary sum is a particular case of sigma. You can, yeah, maybe let's do this very quickly. Not in Agda, but you can do it as an exercise in Agda. So we map in L of some A0, same type was before, maps to, we map it to what? To the pair 0, A0, and then we map in right of A1 to, okay, we should not just say B0, and here we say B1, A. Yeah. So intuitively, this is very clear, right? So we're using here a tag in L or a tag in R to say whether something goes on the left or on the right. And here we replace the tag by 0 or 1. And it doesn't really matter if you call the tag 0 or in left or 1 or in right. Yeah. So you can do actually this exercise, define the isomorphism. So this is, so sigma is the infinitary version of the binary sum. And similarly, pi is the infinitary version of the binary Cartesian product. Okay, so we're running out of time. Exactly when we get to the more complicated definition, which is the identity type. Okay, so the identity type is not really a type. It's a type family. So we have a type here, which is the index in type. And then this produces not a single type as in the examples before. So you can notice that in this example, for instance, we define a single type here, and these are parameters. And here we have a parameter A, and then we have the type family. And we say, okay, we only have one constructor for the identity type. So we write it in infix notation. We call it refl. And refl, given any element of the type A, produces an element of this type family. So, and the intuition is that this is a proof that X equals X. So refl X is a proof that X equals X. Proof that X is equal to X itself. Okay, now what could possibly be the elimination principle? Well, the conclusion, I cannot say is the same as before, because it's not. Before we define a new type, but now we define a type family. But it's very similar to what it was before. So we have a predicate, but now the predicate has to take three things: two elements of the type and two elements of the type parameter and an element of the new defined type. So this AXYP. So P is an identity. I like to call the elements of the identity type, and other people also like that, to call them identifications. In the hot book, they are also called paths, but I prefer to call them identifications. So if you want to prove that the property A holds for all identifications between any two endpoints X and Y, what do you need to do? So that's what you want to show. Yeah, for any endpoints X, Y, X and Y, and the identification P of them, and to show that the property holds. And now this is the magic of homotopy type theory, or also of Martin-Lev type theory, that in order to prove that this holds for all identifications, it is enough to prove that for every X, it holds for a particular identification, the particular identification refl of X. Now, there are two mysterious things here. One is that when I define the type here, I say that there is only one constructor, but then when I speak of it, I say, but actually, there can be many elements in the identity type. Now, where are these elements going to come from? Well, there are two sources of more elements other than refl in the identity type. One of them is the univalence axiom. So the univalence axiom allows you to actually construct identity types which have more than one element. And another source is higher inductive types. So higher inductive types also allow you to do that. And now the magic is that even if you add more elements to the identity type using such devices, it will still be the case that in order to prove that the property holds for all identifications, it's enough to prove it for the reflexive identifications. Now, we are not assuming in this summer school that people know category theory. This is not assumed, but if you happen to know category theory, you may have seen something called the Yoneda lemma. Well, the Yoneda lemma has actually several items belonging to it, but one of them is that for certain natural transformations, although they are defined on all morphisms, in order to know the whole natural transformation, it is enough to know what happens to the identity transformations. Yeah. So even though the transformation is defined for all the morphisms, it's enough to know what happens at the identity morphisms, and then you know everything about it. The situation here is very similar. So in order to know everything about the identifications, is enough to know about the reflexive identifications. And in Agda, you write the proof like this. Maybe we can try this to do this manually. So let's see, this is going to be the F. And then after that, we have the X and the Y and the P. And then we need to produce an element of AXYP. So that's the goal. And then we have this. Okay, so now Agda allows you to pattern match on things that are defined using data. And so we can pattern match on P here. Okay, and now you see, I didn't write the dots before, but Agda wrote some dots. Let's explain what this means. So the dot here means that actually this X is not a variable anymore. This X here has to be the same X as this one. So when Agda is computing, as soon as he knows what the first one is, then you get this second one is this. And the same for here. But Agda actually allows you to remove the dots. So I will remove the dots. Now we need to produce this, but this is that's exactly the hypothesis of F. So we go F, and then we need the X here. Notice that Agda is doing something similar to exactly what we are trying to prove. We're trying to prove that in order to show that this holds everywhere, it's enough to show that it holds on the reflexive identifications. And that's actually what the pattern matching of Agda does. Now, if we come back to the discussion of without K, when you have this option, Agda is going to be much more restrictive in when pattern matching on identifications is allowed. When you say without K, it is allowed less often than by default, okay? And this less often is just often enough so that pattern matching on REFL becomes equivalent to the elimination principle for the identity type, okay? And this is a theorem that Jesper Cox proved. So the implementation of Agda is based on this theorem that he proved.
Okay. There was a question about why X can appear multiple times, and I think a very illustrative example would be how about deleting REFL following that, just have two X's and then equal sign and see what Agda says.
Do what?
So remove REFL X and just write, yeah.
Write what?
No, just keep that field blank and then keep the right-hand side a question mark. So here, or yeah, for example, that's, and well, it's going to give a type checking error, but also basically Agda has this case tree, right? So it has a definition where X equals X definitionally. It asks, does that represent all of the cases? And when you have P there, it does not represent all of the cases. But when you have reflexivity there, it does represent all of the cases via that algorithm.
That's exactly right. Yeah. You can also write it like this if you want. What I prefer to emphasize is the same X. Okay, so that's exactly, what a page wrote in her lectures, not in the same notation, because the notation on paper is slightly different, having the context and the gammas and so on. And this is exactly the definitional equality that occurs in the definition of the elimination principle. Okay, so I plan to show one example, but I'll show you next time. But after you do a few things that should take 10 minutes, then we can show some examples of types. These are not theorems, they are just statements of theorem. Yeah, a type is a statement of a theorem. An element of a type is a proof of a theorem. So nobody knows the proof of the twin prime conjecture or its negation. So the twin prime conjecture says there are arbitrarily large primes such that p plus 2 is also prime. And the way to say that, well, let's first define prime. So suppose we have defined p bigger than, so prime is going to be here p bigger than 2, and then we don't say and in type theory, we say times, we use the Cartesian product. So to prove that something is prime, you need to prove it's bigger than 2, and you need to prove that for any given two natural numbers, if their product is p, then the number x should be 1 or p. Yeah, so that's one possible way to define prime. So here we use this for or, the function space for implication, the identity type for equality, and the Cartesian product for and. And here we are going to use the sigma type for exists. So what is the twin prime conjecture? It says for any given n, there exists a p bigger than n with this satisfying these two conditions. So why do we use there exists represented by sigma? Because here, to show that something exists, you give an example, that's the first component of the pair, and then you need to show that the example you gave, p, satisfies the condition you want, and that's the second element of the pair. But the second element of the pair is a Cartesian product of three things, yeah, and the three conditions you want. Okay, so I'm going to actually define this again more slowly in the first 5 or 10 minutes of the next lecture.
Martín,
other examples.
If you think it takes only 10 minutes to do this, I would be fine with it if you do it now, but it's your choice.
I think there is a maximum amount of time that people can absorb information. Okay. So probably better to do this freshly from starting 5 minutes next time. It will also be good to then as a continuity for the next point of the lecture. Thank you.
Okay, and let's thank Martín.
Thank you.
And are there any questions?
So 2 people raised their hands, and I'll allow them to speak then.
Yeah.
Okay, so Moit, you can speak now. But you're muted. Okay, I'll also allow Ian to talk.
Thank you. Earlier, Martin, I was the one that asked the question about if you could do record with identity types, and you said just initially you didn't think so because that would lead to K.
Yeah.
I was just thinking, does it matter that the identity type is a type family rather than so the one element that we construct is REFL, it's a function that depends on an argument. Like, does that change anything in your answer? I just didn't know if you still agreed with your initial answer.
Yeah, I honestly never thought about defining the identity type with a record before, so because I haven't thought about that. The only answer I gave during the lecture was more a guess than an answer. So
Okay, yeah, I got you. Okay.
we'll have to experiment with it and also perhaps ask the Agda developers.
Okay,
About
thank you.
Yes. But there is another comment which is appropriate about the type family. It doesn't matter whether you think of it as a type family or not. It is actually the fact that you're defining a type family, let me see here, rather than just a type, that allows this seemingly counterintuitive behavior of the type,
Right.
which allows it to have more elements than those mentioned by constructors. Yeah. And in fact, at the beginning of type theory in the 80s and 90s, people were trying to prove that the K axiom. So they were trying to prove that every identification between X and X must be a REFL of X. And they couldn't prove this no matter how hard they tried. And eventually, in order to show that this is not provable, Martin Hoffman and Thomas Streicher produced a model of type theory in which this is not the case. And this is the groupoid model of type theory. So types are interpreted as groupoids. And this can be seen as a genesis of homotopy type theory, except that they didn't consider infinity groupoids. They considered just one groupoids in order to show this. So to repeat what I said, the fact that you are defining a family rather than a type here, it is what is preventing you to show that that REFL is the only thing. So for example, for the Booleans, you can prove that every Boolean is either true or false. For the natural numbers, you can prove that every natural number is 0 or a successor. For this binary sum type, you can show that every element of the type is in left or in right, and so on. But for the identity type, you cannot prove that every element must be a REFL. Yeah, and the reason, one reason behind that is that it's not really a type what you're defining a type family.
So for those first two that you mentioned, is that a definitional quality, or whenever you say prove, do you mean an identification?
Yeah. So as I mentioned before in the lecture, in type theory, a lot of types have a dual interpretation, either as mathematical objects or mathematical statements. Yeah. So when you do the union of two types and you think of them as collections, I think in the mathematical objects. But sometimes I use types like the ones I showed at the end here, which are interpreted as mathematical statements. So usually people use the word proof for an element of a type when you're viewing this type as a mathematical statement. So if I say a proof that X equals Y, is that I'm imagining then the identity type X equals Y as a mathematical statement, and I will say proof. But then that's an identification, yeah? Does that make sense?
Yes. Well, so the reason I asked, I mean, just sorry, since there was a silence, I kind of wanted to continue what I was thinking. We did prove in the last worksheet for HoTT that there is an identification between the sigma type A REFL identified with Z.
Yeah, I think I'm going to after you try this exercise, I'm going to revisit this. I think it's something like this. Sigma, how was it?
So it's like sigma Z, wait, sorry. What was it? For all A, yeah, sigma A, and then yeah, and then the type family is A equal to X, I think, because
Okay,
it's a base path, I think. It's like
Okay.
the pair, you're looking at the dependent pairs A and X equal to A. I'm pretty sure.
Okay, so this okay, so you can prove that a ref something like, okay, so something like this, XP
Is equal to A referral, yeah.
to X referral.
Or
Y referral.
yeah, I think it's A, or yeah, Y referral would be fine. Yeah.
And then P equals Y. Okay, so that's a very good question. So that's counterintuitive, because how can these two things be true at the same time? The
Right.
identity type has more elements than just referral in general, but this equality holds nevertheless. Okay, so that's very interesting. There is no contradiction here, but in order to do that, we will need to understand how the equality in the sigma type works, which is one of the main topics of the next lecture. But basically, there's going to be some transport in the second component, and then you'll see what is going to happen. And also, there's possible to give intuitions about why this is the case. But this takes some time to set up the explanation and then do the explanation. So I prefer to answer this in full next time.
Okay, sounds good. Thanks.
If you want to read ahead of time, some of this is in the handouts for the Agda part.
Good questions. Oh, and I want to remind everyone that we have problem solving sessions tomorrow. I'll be leading the North American session.
Okay, so probably can stop recording. Are you still recording?